Now, yesterday we have talked about something orbiting around something, right? So we have talked about the satellite orbiting around the Earth, the moon orbiting around the Earth, the planets orbiting around the sun, and so on. So today we are going on to the next part of this topic. So we are not relating the circular motion with gravitation. So there's another part in gravitation. So first of all, let's have a concept of field. Now, I think you have heard about, you have learned about the electric field, or you may heard about magnetic field. And also there's a gravitational field. So you may be asked about what is the definition of a field of a force. So field of a force is a region where object experience forces. It can be electric force, it can be magnetic force, it can be gravitational force. But when we're talking about the gravitational field, this is the region where masses experience forces. Now you may be asked about this definition in pair 4. So in pair 4, the definitions or the long questions, the wording questions count for around 35% of your paper. Then actually there's a good news for you, because if you remember those points, you can get all these, at least around 40% marks. So now, let me change some of the words. So let's say there are also questions like the definition of electric field. So that is a region where what the charges experience forces. If you're talking about the magnetic field, so it's a region where the magnets experience forces. Okay. Then you know how to define these three fields. Just look at the screen yourself. Just look at the screen yourself. Electric, magnetic. Not only these three, but what you just need to learn these three. So let's move on. Now if you still remember, in Form 4, you have learned how to draw the electric field pattern. So we also need to draw the confrontational field pattern. So these are the gravitational field lines. So this is the Earth. So all the field lines point towards the Earth. Yeah, it's just quite similar to a negative point charge. Quite similar, but not quite similar. Okay. So these are the gravitational field field lines.
So basically the radius where on my head.
Equally spaced. So if you just look at the Earth's surface, so that means we just take a look at just this part, okay? Now you take a very close look, you take a close look on the Earth's surface. The gravitational field lines will be just parallel and perpendicular to the surface. So they're uniform if it's on the Earth's surface. And that's the reason why your weight is always constant on the Earth surface, on the Earth's surface.做咩啫？我45 kg 啫嘛，你50幾嘛，老師，你50幾 kg 嘛，唔止係嘛？好啦。So this is how we draw the gravitational field lines. And then we need a quantity to quantify the gravitational field. So that quantity we call the gravitational field strength. So you need to be aware of the question. So whether the question asks you to define a gravitational field or gravitational field strength. So there's these two are different things, is it? So gravitational field strength, we use a symbol G, small g. You have used it before. That's 9.81 if it's on the Earth's surface. And this is defined as the gravitational force on a point mass divided by its mass. No. I'll explain now. So let's say this is the Earth. No, this is the Earth. Good. So there's an alien spaceship, okay? Alien spaceship. So you can see that, okay, this alien spaceship is quite large. And if you're talking about the force acting on the spaceship by the Earth, can you see that? Okay, actually, at every point, the direction of the force and the magnitude of the force are different because of the size of the spaceship, and also, and because the distance between the spaceship, that part of the spaceship, and the center of the Earth is different. So therefore, the magnitude of the gravitational force on different parts of the spaceship are different. If we want to find the gravitational field strength, we must use a point mass because we are talking about the gravitation. We are talking about the field strength at one point. Then we must use a point mass there, not like this alien spaceship. Otherwise, how can you find it? Whether you are taking at this point or this point or this point, and at which point of gravitational field strength do you mean? It's difficult.
So why is that point mass flat?
Divide by the mass.
Oh,
Divide by the mass. So that's one question in the past paper asking you something like this. So let's take a look. Not this one. Sorry. No, they didn't ask you that one, but okay, they didn't ask you that one. But this is indeed a good question. But you need to remember it's a point mass. And later on to define the initial field strength. So this is the initial force on a positive point charge per unit charge. Similar. You have a point. So then let's take a look at the formula. So small g is the gravitational field strength. So that is a force divided by the mass of the object. So let's say at this point, you're putting a point mass small m. This is a big M. What is the formula for the gravitational force? You have just learned it yesterday. Yeah, so it's gmm over r squared. So that is a gravitational force, is it? On the small m, on the point mass, on the point mass. So then you cancel out the mass in the equation. Then you can get the final formula for the gravitational field strength. This is one formula that you need to remember. So it's just G big G M over R squared.要計數咩？呢個都冇數字俾你。So let me give you one example. That's a gravitational field strength. Gravitational field strength.
That's GM.
Yeah.
What's the other?
Gravitational force.
Okay. Move on. So this one. Now, you may think about, okay, so the G we take is 9.x1. Actually, we have derived this one yesterday, if you still remember. We did. You still remember you have find my weight yesterday? Yeah. And I show you that, okay, it's if you use a formula GM over R squared, it's just the same as if you're using mg. If I'm on the Earth's surface. Okay. So universal gravitational constant is just a constant in your calculator. Constant. So for then let's take a look at. So let's calculate my weights again. So at this point, you know that G is 9.x1, is it? And I'm 6,378 kilometer from the center of the Earth. So let's say I jump. Okay. Do you know how far I can jump? You don't know. It's 1 kilometer. So let's say I jump to that high, okay, that high. So can you find a G again? The gravitational field strength. Now let me give you, I'll give you the mass of the Earth. And then I think you can still recall the formula of gravitational field strength. So so can you get the value of the gravitational field strength when I'm 1 kilometer above the Earth's surface? Higher. It doesn't matter. You see, can you see it in the formula for this formula? You just need to use the mass of the Earth.
G is 6.67.
You get in your calculator shift 717. 17. No. 9.807. It's still 9.81. You still get the same value because this 1 kilometer is actually much less than 6,378. So that's why when you're on the Earth's surface, you always consider G to be constant. Yeah. Now, so that's why we always take G be constant if you're on the Earth's surface, unless you go to the go outside the atmosphere, then the G may change a bit. Okay. So there's one question in the long. Now, there's one question they ask you. Now, there's one question that you copy down by yourself. So explain why the gravitational field strength G close to the Earth's surface is approximately constant. I'll show you by calculation, but you may be asked about this question in wording. So I copy a question and the answer here. So at the Earth's surface, the gravitational field strength line, sorry, the gravitational field lines are radial. Radial, you know what is meant by radial? I've drawn before. Hey, you just look at the diagram. This called the left-hand side is called radial. And the height above the Earth's surface is comparable. Comparable means, in this case, it means much smaller than the radius of the Earth. It's much smaller than the radius of the Earth. So even if you take the height, you calculate the height, calculate the R in the formula, you still get the same result for G. It's still 9.81. Huh? 係啊。 你做咩淨係影相？
Clarify.
呢個咩？
Okay, you know, forget.
It said in the water.
Oh.
Is your weight the same?
Yes,
Really?
yes.
Alright.
What about outside the ocean? So we have to copy like that.
But inside the water, there's another upward force acting on you. You feel that you weight less, but it isn't. It isn't a way to lose your mass. Okay?
In the water. Oh, we did.
You think about all the mammals living in the water. Then you know you gain weight. Okay. Mammal. Well, it's a mammal.
You know.
It's shark is a shark is a fish. Dolphin is mammal. And that's actually one way to remember is you think about how its tail move. Fish move like this. Mammal move like this. 係啊，咁分嘅係啊，唔係其中一種分嘅方法咯，唔係 most of the case 啊，not 100%。
It goes inwards. No?
It's go inwards or outwards. So that one is a radial inverse. Radial inverse. That means point towards the center or pointing away from the center. It's called radial. So the pattern is radial. Okay. Let's continue. So you just finished this part. Of course, you know on different planets, the G is different. On Moon, it's just around 1/6 of that of the Earth. So let's go on to the next concept. So that's about the energy. So I think you have learned, you know that there's a gravitational potential energy. Now you know that there's one formula for that, is mgh. mgh. mgh, you know that. But that formula is only for objects near the Earth's surface. If you're talking about a satellite and the Earth, we cannot use mgh. Because if you're talking about a satellite and the Earth, the weight or the gravitational force is not a constant. We can't use mgh. We can't use mgh. Then we are going to derive this formula now. So here is the Earth. Right. Because you have two factors. The Earth is crashed by you. Okay. So this is the Earth. In biology, have you learned water potential? Water potential.
I don't take bio.
Oh, hydrotonic.
Yeah, water potential.
Yes.
I think you have that concept, but you didn't have the formula for that one.
Yeah.
係啊。
When we
Sir,
take
why did you
one-
ask everyone else before me? You trying to say I'm stupid? Like, I'm the only one here that takes bio. Why are you looking at someone?
No, they have learned.
I am.
Did you take biology in our GCSE?
No, it's so lame.
Sir, it's all been bullshit.
Biology is so easy.
No.
That's why we got paid. It's for dumb.
Easy.
No offense.
It's
Ah.
for failures.
What?
Most people do biology or people who want to take a science subject but doesn't want to take chemistry or physics, so they take biology.
Bio is much
Not
harder.
you like that.
Bio is so much harder than physics, okay? Fuck
Not
out.
you, not you. They never changed the wording.
What?
Recording is
Bio is
recording.
harder than chem and physics.
Yeah.
You have to remember?
You just remember.
My hair goes gray after learning that shit. No, you just remember? Try.
Then you can
Impossible.
you save the money for it.
No, they asked about which one the extras in the exam. You know, we never learned that.
That's-
Hi, how?
It's
Let's
how
move on,
DNA
let's-
replication and how they disperse after. How the fuck am I supposed to do that?
Now let's move on. Hey. Peace. So we do have some assumption first. Now, if you still remember for MGH, where is the GP zero? At the ground level. But for general case, we let the infinity to be zero. So that means at that point, the small m and big M do not have any interaction. So they don't have any gravitational force. They're not acting forces on each other. So at this point, okay, I can't draw the object in infinity. I'll just draw. 人哋點畫嘅咧？我唔好記得啦。something like this 啊，係。So that means they are separated to infinity. So at this point, we say that the GPE is 0 at infinity. So that at that point, the R is infinity. That means the separation between these two masses is infinite. And you know that the gravitational force is an attractive force. So when these two objects, if these two objects get closer to each other, so let's say if there's two masses, and then if you just there are these two masses in the space, and then you release them from rest, what they will do, because they're attractive gravitational force, they will attract to each other, and then they will moving faster and faster and faster until they collide. Is it? Because there's an attractive force towards each other. So they will get closer and faster and closer and faster to each other. Huh? I'm just 45 kg. You are around 60. You're around 60.
10 kg, lucky tank.
Sir, you're underweight.
Yes, I'm underweight.
Wait, sir, so why in space is everything not like stuck together?
Because you think about, let's say in this universe, only there is a sun and the earth. Just the earth is still orbiting around the sun because although there's an attractive force, but that force is responsible for the circular motion of the earth.
So obviously like a billion years is the Earth and the touch the sun.
that's another story. Actually, the Earth is getting away and away from the sun because of two reasons. Yeah, moving away from the sun. One reason is the universe is expanding. Another reason is, I think this is so difficult to talk about. So it's about some tidal force, and then we make the Earth moving away from the sun. Whatever, you don't need to know why. So the next one, now, I hope you first of all you understand. So let's say if the small m has somehow by itself moved to here. If you push the small m a bit, and it starts to move things towards the Earth, and at somewhere with the distance r, the GPE is actually negative. So the GPE is negative. You need to understand why. Just go back to the example of the two objects in the space. At infinity, the GPE is 0. If they're getting closer to each other, they are losing their GPE and convert the GPE to KE. Is it? They're attracting to each other, they're getting faster and faster. And if they lost GPE from 0, that means the GPE becomes negative. Understand? At infinity, the GPE is defined to be 0. And as they get closer to each other due to the gravitational force, and that means they are gaining the KE. So where does the K come from? GPE. GPE. There's no other energy. So they convert the GPE to KE. Yeah. So GPE decreases from 0. At infinity 0. So it decreases from.
If it's less than 0, there's 0 GPE. Where does the KE come from?
You push the small m a bit. Let it to move towards the Earth a bit. So otherwise, I can't give you this story because if you're talking about the objects, yeah, you just need to know that the GPE will decrease when it gets in closer to Earth.
So what's that 2 lines?
I mean at infinity, separated. Never positive. Always negative.
What they get pushed the other way.
Then they're getting further and further away from each other. And we are going to derive the formula. For GP, we use a symbol, the big U. Bless you, okay. Is it negative? Is your result negative? Uh-huh. So now, you know there's an attractive force acting on the small m. And then this gravitational force will do work on the object to increase its KE. The symbol for GPE. Now this bracket R, it means at the point R, okay? That's the way how we write the function. or you can write it in other way, okay, as you like. So it's moving from infinity to R. So why we need to do the integration? Because the force is not a constant. So we need to, if you still remember the formula of work done, it's force times displacement. So in this case, you need to integrate the force with the displacement. Now, indeed, there should be some negative sign here. I just cancel them out. I don't want to explain why there's a negative sign here. But so this negative, it means attractive. And this negative, it means the external force, the work done by the external force. Then the work done by external force, that is the definition of GPE, the PE. Whatever, you just forget about it. Are you able to do this integration? Why not? You have learned it already.
Integration is fun.
Have you learned about integration?
I forgot it all.
Yeah, not this level.
Oh, algebraic.
Only
Well, this one is R to power negative 2. You learned that R to power n. Have you learned that? X to power n. X to power n 係咪? Do you know how to integrate this one?
Yeah.
What's the result?
X to the power.
Just the same. N is just name 2. It's just a constant. Take it out.
You can do that?
Why you can't do that?
Because for us, you can just take it out.
You can.
Really?
Yes.
Really?
Yes. Then how you integrate this one?
You don't specify that?
Why? But you are just given this formula, not 2x to power n. That's why you can take it out. You are. Why is difficult? Why is difficult to understand? Now, you are just given. You just have learned this how to integrate this one. Is it? You haven't learned how to integrate 2x.
No.
You don't have a formula for 2x.
No.
You don't.
Sir.
You just listen. You just have a formula how to integrate x to power n, not some constant times x to power n. So how we deal with those constants? We just take it out from the equation. You take the 2 out from the integration and then you integrate x with respect to x. All right, next week we have tutorial class for math for 5 days.
I have nothing to
I
say.
swear.
Oh no, you should.
I feel like my math is so shit.
It's recording. So do you
Really gonna send this. You're making dumb parties. You're like,
Sir, you're gonna have to edit this a fair bit.
now let's do it. Okay, you can do it. Okay. Now this one is and then negative plus 1 is negative 1 and then divide by negative 2 plus 1.
I completely forgot how to. You add and then you put it over, right? Yeah, so under.
你咪學咗definite integral and you substitute R in the formula
So you can write. Oh, never.
and then it'll just give you R. If you substitute the infinity, you know 1 over infinity will give you 0.
Oh,
So that's how we get a final formula. Now you don't need to know the proof in physics, of course, but I want to show you. Why you are so late?
It's the same process there.
Well, that person only once 1 hour. That's only one bus per hour, is it? Now then let's take a look at how we can use this formula. Then let's move on.
Really bad at class. If you explain how you get from zero to
No. This one, R negative 1 divided by negative 1 R x to power negative 1 is 1 over x.
X to the power of
Negative 1 is 1 over x.
Why is it
Over one is just the same.
It's just in negative r to power negative 1.
Wait, something over negative. What did you say?
X over negative 1 is negative x.
Oh.
You need to think about that. 好啦，唉。好啦，now let's think about a case. So let's say I'm throwing a ball away from the earth. Do you want do you want to substitute the values? If not, we just keep it as a variable. So let's say, okay, this is still the earth. Okay, this is still the earth. So the radius of the earth, we still take it this one, okay? So I'm throwing a ball upwards with the speed. No. Now, I don't think you be. I think you. I don't want to show off there, but I can really throw the ball 1,000 meters per second.
Wow. Why did you just pick up physics?
I missed a chance to get into the Olympics. It doesn't matter. Let's move on. So let's say this ball will just go up to the sky. But let me push the ball a bit harder. So let's say 10,000. 10,000. Yeah. Because I'm so strong. Oh. So in this case, I would like to find the height of the ball above the ground. Now, normally, if you think that you can use the formula mgh, let me show you the result. Let me show you the result. So you say mgh you half m squared, is it, of the ball? And you can get the height to be v squared over 2g. Using your calculator, you can get the result. Can you give me a second? I think I'm pushing it a bit too hard. The ball can leave. It's still fine. Okay. That's right. Let me make it smaller. Let me make it smaller. Because I want to get back this. I want to get back this stone. No, this is gold. Okay, gold. Okay. So let's say 5,000 meters per second. Now, if you're using the formula mgh equal half m squared, then let's see what you can get for the height. So 1.27 or 1.3 times 10 to the power 6 meter. That's much larger than the. But in terms of kilometer, it's 1274 kilometer. That's it. But that one is actually this is not correct because we cannot, if the speed is that large, we cannot use these formulas because the g is not constant. It's not a constant anymore. So how can we find the height? Now we need to use the formula we have just learned. So at this point, you know the speed is 0. Now we're still using the energy. So let this point to be A, this point to be B. I think it's not difficult to understand that the energy is conserved in this case. So that means KE at the point A plus the GPE at the point A, that will equal to KE at the point B plus the GPE at the point B. Understand? So that is the initial total energy equals final total energy. So then we just write down the formula. So for kg at the point A is half m v squared. Now the GPE, remember, we have derived the formula. It's negative gmm over r. It's negative gmm over r. Now you don't need to take a look at the textbook because in the textbook, it didn't give you a formula of GPE, but give you another one. I don't like that one. Actually, the student will prefer. I introduce this one first. Okay, I introduce another quantity, which is quite dumb. Small m is the mass of the stone. No, you can cancel out in this formula. So it's negative gmm over r. Now this r is the distance from the object to the center of the Earth. So it's 36378 times 10 to the power 3. So at the point B, the KE is 0, and the GPE, remember the R, this is the distance from the object to the center of the Earth. So you need to use the radius of the Earth plus the height h. So then you get the height to be 1592 kilogram. Kilometer, sorry. Kilometer. We cancel out from the left hand side, right hand side. You divide the small m on the left hand side, right hand side. Answer 你教下佢，你教下佢，佢唔知點樣 cancel m，我都唔知點樣講。你有聽到講咩？我唔知佢，你呢個初中數嚟嘅喎，你去升中六你都唔識，唔係左邊右邊個 m 咪 cancel 咗咯，你仲可以點？I just show you in kilometer because you can use meter, you can use meter。唔係嗱，我想問你一樣嘢先。例如我話條式係 ax 加 bx 等於 cx， 你點樣約走 x 去啊？你係咪你約完 x 係咪 a 加 b 等於 c 先？你識唔識 factor out 個 x 出嚟㗎？咁 a 加 b 咪等於 c 啊？係嘛？得 G 唔得啊？左邊有，左邊唔係。OK。And then let's take a look. So let's take a look how fast I should throw the ball such that it can escape from the earth. So when I say escape from the earth, it means it never come back. It will never come back. So in this case, you know at the point B, then at the point B, it will momentarily at rest, and then it will be attracted by the earth, and it will go back to earth. Much further. So what do you mean by escape from the earth? That means the object can go to infinity. That it can escape from the earth. So then we are going to find that speed. That speed, we have a name for it. We call it escape velocity. And I would like to derive a formula first in terms of the numbers. So you are given the speed to this object, and this object is 5 to infinity, and then can rest in infinity. RIF, okay. Hmm? 你講咩？你中文講一次。 escape velocity. So this is a velocity. Now you are not asked about this definition. So this is a minimum velocity to escape from the Earth.
For the question before,
Hmm.
I got a negative.
I think you didn't put the negative sign here. Oh, sorry? So this is a minimum speed velocity to escape from the Earth. Escape from the Earth, that means it will never come back. Okay? No. No. We're now talking about the objects moving around, moving in a circle around the Earth. Now, we take a look. So at infinity, the GP is 0. This is at infinity. The KE will also let it to be 0. If the KE at infinity is 0, then that means we are throwing it at the minimum speed. Then we can get the formula. That is half me squared. But here is the radius of the Earth. So it's still the formula KE plus GPE equals KE plus GPE. So now you make the V be a subject of the equation. Now, so this is the formula for the escape velocity from from any object, from Earth, from Moon, from Mars, from the Sun. Oh, it's okay. The big R is the radius of that planet or that object. Then you take a look at you substitute the value. The mass of the Earth is 5.98 times 10 to the power 24 kilogram. The radius of the Earth is 36378 kilometer. And you find a V, it will be around 11.2 kilometer per second. So that means if you can eject any object on Earth with this speed, then that object can escape from the Earth. Okay. That means if you think about those satellites, I mean those rockets carrying a satellite, let's say want to go to Jupiter, then almost the rocket can achieve this speed at some point. But if you study astronomy, we know that okay. Sometimes it does not need that high speed. It can make use of the gravitational force by other planets to accelerate. Whatever, so it's not in our syllabus. So we have introduced the GPE, and also have introduced how to use it to solve some of the questions. Then let's go to the last quantity you need to know in this chapter. And then we can make a summary after that. So the last one is called confrontation position. To me, this term is totally BS.
Yeah.
Let me write down this definition, okay? So this one is defined as the when you define it in exam paper, you need to define it very indeed. Mm. 抄住先啦，你唔抄你唔記得噶嘛，你唔會齋望你記得噶嘛。你抄完都記唔到，咁你再抄10次咯。It's time you remember 啦。You have less than 1 year, and you are going to take the exam. You don't have me 噶啦 next year.
What's that supposed to mean?
嚇
The other teacher could be great.
？OK 咯，so that's why I leave 咯，係咪？
Don't believe your friends will not told.
Yeah, that's good. That's
So where do you live?
When?
Where?
Where? No, go to another school.
Which one? You where you live,
Now for this one we use a symbol, but this one we use a symbol phi. This one we use a symbol phi. Phi, 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 phi. And the formula for it will be actually we finished this part, and now I think it's almost the end of this chapter. Cool. So the formula will be net Gm over R. So that is a gravitational potential. Huh? Similar, not same. Now, actually, in total, we've learned about 4 quantities: gravitational force, gravitational field strength, gravitational potential energy, and gravitational potential. In total, 4. Just a second. I want to meet my colleague there. Oh? It divided by mass. Now, you may think that, okay, wow, there's so many formulas, so difficult to remember. So we are going to make a summary in this part, in this chapter. So for those 4 quantities. So let's take a look at, in total, we have learned about 4 quantities. So let's draw some perfect rectangles.
Make sure you're recording. It's not gonna just like it.
Yeah.
Thank you.
No. So you now we are drawing some perfect rectangles. Hmm? 4 perfect 啫嘛，I didn't say 4 identical 啊。好啦， so it represents those 4 quantities we have learned. So the first one, I think the most easiest one will be the gravitational force. Gravitational force. So for the formula is Gmm over R square, is it? So that's the formula of the force. And then the next one is the gravitational field strength. So it's GM over R squared.
I'm not going to give you
So then, from the force to field strength, we divided by the mass. Is it of the point divided by the mass of the point mass? Of course, on the other hand, we multiply by the mass. Okay. Then take a look at the energy. Confrontational potential energy. We have the formula U is negative GM over R, but GMM over R. So from the force to energy, if you still remember, we do integration. So we do the integration to get the energy from force to energy, from force to potential. And here, do you know what is the inverse operation of integration? Yeah, that is a differentiation. So from energy to force, you need to do a negative differentiation with respect to R. Or now this is also one formula in your book. So that is F U to negative delta U over delta R. You know that means differentiation. Delta something over delta something, it means differentiation. That's a formula how we relate the force and energy. How we get the force from energy. Yeah. So from potential energy to confrontation potential, you know we divided by the mass. So, and then by your 130 IQ. So can you tell me what will be the relation between the field strength and potential? Hi. From
Integrate.
yeah. So you see force divided by mass, you get field strength. Potential energy divided by mass, you get potential. So that means the field strength and potential should also have the same relation as force and energy. Understand?
So it's exactly the same.
Yeah. So I'll just Why there's no copy and paste? Why? Because in
Sorry, which you don't have to draw the right.
because my in good notes I can copy and paste. Right. I can save the ink for drawing. All right, that's a relation of these four quantities. I think it's very clear. In the middle. Where do you mean middle? This one to this one, not the differentiation. Now, here in your textbook, actually, they also give you this formula, this one. I think you have read the.
Just integrate it.
You don't need to integrate. You don't need to integrate. I'll just tell you the relation, but you may need to do the differentiation. I mean, from the graph, you find a tangent line, and then I'll show you the past paper tomorrow. But you may need to do the find the gradient and then find the value to find the force or find the field strength. Now I think you have read the textbook, and you may notice that in the textbook they didn't give you this formula. What they give you is the phi. They say the phi is energy over mass, but in most of the past paper or in most of the question, you need to deal with the energy instead of the potential. So that's why I introduce energy first, then potential. I think potential, the concept of potential is quite difficult to understand, but energy is okay, man. And you know what I mean later on if you do more past papers. Then we finish this chapter lah. Nothing new lah, nothing else lah. Very effective, come on. Our lesson should be effective. Maybe we have.
Yeah, no, that's
No, if you're gonna like talk to people in a class, right?
No, yeah, that's what I was just. You don't seem like the one dragging us down. You don't seem to be the one dragging us down.
Oh, you cut out Jasmine. Oh, fuck.
I didn't make